Thank you very much. Thank you for this kind invitation to the ICTS. It's always a pleasure to come here. Now, the lectures are on, as you can see, on generalized hydrodynamics. And of course, in this conference, we have experts on generalized hydrodynamics, which presumably know more about the subject than I do. But those are not the people I'm addressing in these lectures. I basically assume that you never heard really about generalized hydrodynamics, and I want to explain you the concept by using one very specific model, namely the classical Toda lattice. Okay? And the good news is that during this talk there will be only one single Hamiltonian. I'm just going to look at that one system, okay? And the Hamiltonian is very simple. So let me just write down first the Hamiltonian. So you have Hamiltonian H. So it's a lattice system. So you take a summation over J. You have the kinetic energy, and then you have an exponential interaction. And that's how it is. So this is Toda, and he discovered the system in 1967. And the origin of his studies was that, he was familiar with nonlinear wave phenomena, in particularly traveling waves and solitary waves. So you have waves which are traveling, let's say, in a one-dimensional channel, and maybe you have sort of two peaks coming along, two solitons, and they interact in a complicated way, but then eventually they disintegrate and sort of move more or less unchanged in their shape towards sort of outgoing velocities. And he was wondering whether a similar kind of phenomenon could appear if he looks at a discretized version of a wave equation. And very naively, you might think, that's totally impossible because, this idea of this smooth wave moving and then sort of, colliding. This sort of looks as if it might be destroyed by the lattice. But he discovered, no, that's not the case. And you can actually write down a lattice system and you still have this kind of solitary waves. And of course, then very soon, people conjectured that the system is actually integrable. So that's an integrable system. And I will say a few words about integrability. Before continuing, I want to sort of emphasize that it's really a lattice system. You see, what is interacting are the particles. So it's in particular, it's not permutation invariant under the labels. You have first labeled the particles, and then, with neighboring labels, the particles are interacting. But for me, the momenta and also the position of the particles, they will be always in R. Okay, of course, once in a while, one might have to do constructions, where rather than looking at the infinite lattice, which I indicated over here, I somehow have to take some finite volume. But finite volume doesn't mean that I take, Qj in a finite volume. Rather, what I do is I will simply cut off the sum over the number of particles. So maybe later on I will, go only from 1 up to n or so, right? It's a lattice system. So it's sort of a slightly different from sort of like a real one-dimensional fluid where you have, where you have interactions which are invariant under permutations. Now, so this generalized hydrodynamics of the Toda lattice is actually something which is quite recent. So there are actually 3 papers which you can look up, which all were published sort of basically to the beginning of this year. So there's a paper by Benjamin Doyon, there's a paper by Dani. I don't know whether he arrived, but it's announced, and then Pao and Joel Moore. And also there's a paper by myself, and all these papers are 2019. And now you might have the question, how come that, I'm putting here 3 papers which are just published, and I'm using this sort of as material for a general or sort of introductory type of lecture. Now, the point is that this is sort of a discovery over the last, 4 or 5 years, that this generalized hydrodynamics is a generic structure which essentially holds for any type of these integrable systems. I'm just looking at this very specific one, But once you understand it in one particular case, you have a good chance to understand it for all other cases. Of course, there are complications depending on the particular system, and you have to sort of think about anew. But basically, you can think that the generalized hydrodynamics follows always the same pattern. And therefore, what I'm sort of my philosophy is that I use the Toda lattice, you know, what I call as a roadmap. You see, it has all the complications. You see, if I would take an ideal gas, for which I can also write down the generalized hydrodynamics, it would be pretty useless because, you know, it would not have the complications of a truly interacting integrable system. But the Toda lattice has all the features which we know for the general case. And so if you understand Toda, you know, that's a very good starting point for understanding more complicated system. And another feature, which at least to me, I think it's really a simplification. It's classical, so we have a much sort of simpler intuition. And of course, you know, many of these things will be discussed later on during the conference, and then there will be lots of quantum systems, and then you can sort of see what the correspondence is. But for today and tomorrow, I will just stick with the Toda. Okay. Now, it's just one Hamiltonian I emphasize, but we have initial condition. Yes? Excuse me? I'm only looking at this Hamiltonian, only at the Toda lattice. Yes. Yeah, that's right. Yeah, I can, you know, I'm saying the structure is general. I mean, you know, it applies to other integrable systems, XXC models and delta Bose gases and all kind of other systems. I'm just saying, but I will not cover anything of this during my lecture. I will just look only at this one particular Hamiltonian. Yes?
Is generalized?
Yes. Okay, that's a good.
Generalized?
Well, it's generalized because you generalize from a few conserved quantities to infinitely many. This is what means generalized. And since you're asking question, one thing which I should emphasize, you know, of course it's clear from the way I've written, but the QJs are not ordered, right? I mean, so, you know, it's not that sort of the Q2 is less than Q1. I mean, there's no constraint. It's just as written, okay? All right, okay, so let's see what else I want to say. Yeah, okay, so it's just one Hamiltonian, but there are initial conditions. And so let me just sort of put the kind of initial conditions which we maybe want to study. So there are initial conditions. And the first thing, I mean, you know, in this audience, I think that's fine. I mean, the first thing, of course, you have temperature zero. So, you know, temperature zero means that I just take a uniform lattice or equal space, and then I can look at sort of finite energy sort of perturbation of that particular system. I mean, for instance, if I look at the solitary wave, this would be such a kind of finite energy perturbation of a regular space system. Now, these things have been studied ad infinitum. I mean, of course, Toda had studied this already, I mean, very much. I mean, so there's a book by Toda, which is actually quite informative on nonlinear lattices. And when you look in his book, you know, this is, I don't know, 400 pages, and 390 pages are about zero temperature. And then there are 10 pages where he just studies, you know, sort of the thermodynamics of the thermal state of the Toda lattice. So it's clear that you know, and then there's huge, I mean, you know, physics work. I mean, there's, you know, mathematicians sort of have investigated this kind of object in great detail. But we want to do something different. I mean, we want to do sort of something which you would think of something like positive temperature. So typically you have things like an expanding cloud. So, you know, maybe, so if this is your X space, and here I'm just plotting a density of particles, maybe you sort of, so out here, maybe I have them equally spaced, but then I put many particles in one hump and maybe many particles in another hump, and then I can sort of say that these two macroscopically, you know, this consists of many particles. Objects are actually colliding, and so you want to know what's happening in this particular case. That would be one case. Or then the other one, which is sort of very popular, is you do the so-called domain wall boundary condition. And in this case, I mean, you imagine that, you know, somewhere you have your origin over here, and then you prepare your system in thermal equilibrium with one particular temperature. So now I'm plotting the energy density, if you want to. So the energy density out here will be constant. I mean, so this is, let's say, the temperature T1, and then at the origin you have a jump. I mean, this is what people call the domain wall, and then maybe you have another temperature out here, temperature T2, and so of course if the temperatures are equal, this is a stationary state and nothing would change. But if I make the jump, I mean, then this will be time dependent. You can ask yourself, how is this jump smoothing out? I mean, is it moving to the right, to the left, et cetera, okay? So that would be another thing. I mean, you can also look at small perturbations of an equilibrium system. So, again, I mean, I'm drawing this, let's say, for the energy. So here's my X space. So I imagine that I have a background which is perfectly homogeneous. So let's say this is a thermal state. And now I perturb this, but not in such a manifest way, but I'm sort of putting a little perturbation at time t equals 0 at the origin, and then the question is how is this going to propagate, and what kind of profiles are you going to see later on? Okay, so all these problems can be handled. I mean, to some extent. I mean, generalized hydrodynamics doesn't answer everything, but I mean, it can be very, very well handled by generalized hydrodynamics, and of course, the small perturbations, because it's sort of small perturbation away from a stationary state, can be handled by the linearized version. I mean, my emphasis will be very much on the general structure of this generalized hydrodynamics, and so presumably I will never get to any one of these concrete applications. But I mean, this is the kind of problems which you would really like to get an answer, and I think. I mean, people, of course, in particular, the small perturbation is something which people tried to do already in early 70s, in the 80s, but they just couldn't go anywhere. And the reason is because there was no theory. And I believe that at least to some extent, we have now sort of a reasonable theory to handle all these kind of things. Okay? And then for other systems, there are experiments and all kind of things. So I will not go into this. I mean, I'm really sort of I'm really sort of emphasizing on the structure of generalized hydrodynamics. Okay, very good. So let me see. So, well, I mean, you interrupt me whenever there are questions, and I've prepared here some notes, but we have a lot of time, so we can discuss questions. I mean, very easily. So No. I prepared the initial state and I put some extra energy at the origin, right? I mean, the difference between this one and this one, you see here sort of like a macroscopic perturbation, and here's just sort of order 1 perturbation. So I just deposited a little bit energy at the origin, and then I just wonder how it propagates. Okay. No, I mean, yeah. It's a particle density, or yeah. I mean, I don't know. I mean, this. I think here I was thinking about the density of particles, right? Well, in terms of the Qs, I mean, you basically mean that I mean, in terms of the Qs means that you put lots of particles very close to each other. This would be one peak, and then you have another one which is very close to each other, and then here maybe you put in between sort of like a uniform lattice. What it means. Yeah, then I'm thinking actually sort of a statistical initial condition, right? It would be, let's say, a thermal initial condition. So in both in these cases, I mean, so here, I didn't specify. Of course, you can also think of this as a random initial condition, but here, I mean, clearly, I was thinking in terms of temperatures. I mean, so both cases, I mean, the initial condition would be random and distributed according to the corresponding thermal state, right? Okay, so the first thing which I should discuss with you is the notion of integrability. And of course, this is sort of presumably you learned this in your class on mechanics, or at least some advanced class in mechanics. And so let me just sort of say a few words about this. So let's now cut the sum, let's say from 1 up to n. Now I have n particles. And then you have conserved quantities, which I label as Q, I guess super N. I mean, just to sort of make sure that, you know, this is not an argument. I mean, it's just that's the label of the conserved quantity. And well, I mean, for N particles, if the system would be integrable, I mean, what you learn in your textbook is that you will have N conserved fields. So if I take this quantity and if I compute the Poisson bracket, then this should be equal to 0. And the other thing which you require when you look in the textbook is that Qn and so Qn, you know, are functions on phase space, right? A phase space of N particles. And then I do the Poisson brackets with Qm. It should be in involution. I mean, so this Poisson bracket should be equal to 0. And you see, if this is the case, and so let's say that the N goes here from 1 all the way up to capital N. And if this is the case, I mean, then you can use the Q's, so to speak, as your new generalized momenta. And then what you will see in phase space are these tori. I mean, so you know, the tori are labeled by the values of the conserved quantities. Once I fix their value, I mean, of course, it's 2n degrees of freedom. I mean, no, 2n dimensional phase space, and therefore there's still some motion, but the motion, once you have this structure, will be on this tori, right? I mean, so this is what you learn, and that's certainly correct for the Toda. I mean, this is correct. In fact, Toda conjectured and so forth. He was sort of a numerical person at the time, very famous because, you know, he was sort of brought, I mean, sort of, you know, numerical computation into dynamical systems. I mean, now we are looking, you know, a long time back. He did sort of Poincaré plots, and then he discovered that presumably for 3 particles, it's also integrable. And actually, the general proof that you know, that these relations are satisfied actually by Henault and Flaschka independently. And I mean, you know, Henault is a sort of very amazing computation, but Flaschka is sort of, I will tell you what Flaschka is because we will use it very heavily. And so this was 1974. Okay. Now, it turns out that, you know, this motion on tori, you know, it looks very impressive. And then you think, you know, then you know, one has sort of very concrete description of the dynamics, and then you can solve everything. But that's a total illusion. I mean, it's nice to have this, but, you know, I mean, this tori structure, I mean, you know, we don't really know how to explore. Okay? So somehow this is maybe anyway. I mean, you know, whenever you look at any one of these investigations, I mean, the fact, of course, I mean, you are using somehow the integrable structure, but not in the way as I've written down here. And so there's another bad point about this definition, namely, it does not work for quantum systems. And that's sort of bad news because, after all, we want to apply this scheme also to quantum systems, integrable quantum systems, of course, right? I mean, and the reason is clear. You know, when you look at these definitions, I mean, you know, any eigenprojection of the Hamiltonian would satisfy these conditions, right? And therefore, you know, any quantum mechanical system, at least if I take naive description of these things, would be integrable. And I mean, that might be a correct statement, but it's not so terribly informative, okay? So now I want to use a different definition, which, of course, for the Toda lattice, it decreases. I mean, whether it decreases in general, I mean, nobody knows. But it's sort of a definition which is sort of, you know, adapted to this generalized hydrodynamics. And so I now will use sort of a slightly different definition. And the point is that, you know, there is this notion of locality. I mean, that's something I think those people who attended last week, I mean, you know, you heard this being emphasized, and of course I will emphasize it again. And so now I will use this terminology of conserved charges. I mean, you know, this is just sort of another word for conserved quantities. Okay, so here are my conserved charges. Yes? Just a moment, yes. Okay, now, yes. Yeah, you just replace this by commutators. No, I mean, you know, so I make this definition by you know, just for some quantum mechanical operators. You know, these are functions on phase space. So I just, say a quantum system is integrable if there are, operators on Hilbert space for which these commutation relations are satisfied. Well, that's fine. And then you just take the eigenprojection of your energy. There's just too many. I mean, every eigenprojection will commute, right? I mean, so and it doesn't distinguish between, it's totally, I mean, for every system it's true, right? I mean, well, two-level system, then you only have two, but, I mean, it's sort of a... Yeah, no, you will see in a second. So I'm going to, I will write down for you a definition which works both in the classical and in the quantum case. Okay. All right, so there's this notion of conserved charges, which again I call by Qn. And formally I'm using, the same notation as over here. I mean, it's an infinite sum, which, as such is sort of, maybe not well defined, but if you look at commutators, they're well defined. And so anyway, I mean, I'm just using this standard terminology. And what I mean is that they have a local structure. So, there will be a sum over my whole lattice, let's say. And these conserved charges have a density. And this is labeled by the lattice index J. So if you're not familiar with this notation, just look at this thing. I mean, obviously, the H is the sum of single side terms. Well, in fact, referring to two sides here. So this would be the energy density. And I'm just saying that I'm now looking at not just any object which commutes with the Hamiltonian, but an object which is extensive and which is sort of a sum of local terms, just like this one. You see, this is a strictly local term. If once I fix the lattice side, it only depends. There must be a square here. It only depends on the momentum at that side and at two neighboring lattice sides. Okay. All right. So now we have these objects, and now for this, I require so now okay. So first of all, charges. I mean objects of this type, and now I have to explain you what means conserved. In conserved, it means now that it satisfies a local conservation law. So let me just write this down. So I mean, I always think about the Toda lattice, right? I mean, so of course the definition is general, but so now I look at the density. So this is a function of time because it's evolving under Toda, and then the claim is that there is a current at lattice side J plus 1 minus at lattice side N. So it has sort of this different structure. Okay? Now the observation is that the Q's I require to be strict. So maybe I really should write this down. I mean, so this is local. And of course, then there's sort of this notion of locality. But for me, local is really strictly local, right? I mean, it just depends on a finite number of lattice sides. Okay? And now, if and our Hamiltonian is obviously very local, right? I mean, just the two neighboring lattice sides. And so, if you have to work out this, you have to work out the Poisson brackets, and then it's clear that this quantity here will also be local. But the fact that it can be written as a difference, of course, is a very, very strong constraint. I mean, not anything which I just construct will do this. But if I find one by luck or whatever, some intuition, then this I will call a conserved field. Now, this is the definition which is from the beginning for the infinite system. Right? I mean, so of course, you can sort of do finite approximations, but I want to do this really for the infinite system. Okay. And now the assertion is that so now the question is how many conservation laws do you have? And so then the integrable case. So the integrable case would be that I have an infinite number of conservation laws. So then the n goes, let's say 1, 2, etc., all the way up to infinity. And in the non-integrable case, you try very hard, but then the list stops maybe after 1 or 2. I mean, or maybe 3, and then it finishes. Okay. Now, for the Toda lattice, of course, I will come to this. I mean, this version is actually satisfied. I mean, so in the Toda lattice, so let me first write this down and then we'll make some comments on this. So for the Toda, I mean, there will be explicit constructions of these QNs. Let's say their density is 0. Okay, and indeed, I mean, the n goes from 1, 2, etc., all the way into infinity. And the Qn actually is supported so supported means, you know, on which kind of variables does it depend? And so now I'm looking at the density at the origin. So it will depend on the neighboring sites in an interval which goes like minus n over 2 divided up to n over 2. And so, you know, you have this naive idea when I do the explicit construction, as I start, let's say, from n equals 0, it will be very local, and then you know, I keep, and as I increase the list, I mean, the support becomes sort of larger and larger. But at any given n, it will be strictly local, and of course, this list never stops. And in the non-integrable system is so. Now, there's one very deep question behind. So this definition makes perfectly sense also quantum mechanically, and you can convince yourself that you know, I mean, it's a very strong constriction. I mean, a very strong restriction. I mean, it's not so easy to find these conserved quantities. And they're sort of a somewhat puzzling sort of separation somehow. That you know, at least when you look for examples, we seem to be either sitting in this case or sitting in this case. If I take any one of our systems, either it's sort of, you know, non-integrable with a few conserved quantities like 1, 2, or maybe 5 or so. And then there's the integrable system where it's automatically infinity, right? And then just a moment, and you know, I mean, maybe it's just sort of the way that we look at it, and maybe, you know, we are just not exploring, you know, this somewhat vague space of large, you know, many Hamiltonians, but at least empirically, you know, there seems to be this very clear distinction. If I look at sort of one of the typical systems which you would study in you know, whatever, you know, condensed matter physics, let's say, it's either of this type or it's of this type. Now the labeling, you know, I put here n. In other cases, maybe the label n might be not so convenient, and you will see that I'm going to change this later on very quickly. I mean, so you know, this is sort of more indicative, and for any concrete system, there might be sort of an optimal labeling, which I don't want to indicate here. For the Toda, I mean, this is a very good start. So now there was a question. Yeah. Well, I mean, they should. Well, okay. I mean, you're worried about functional. They could be functional with others. Yes. No. That. So somehow maybe I didn't say this very clearly. I mean, you know, in this list you should be really different functions, right? I mean, so in fact, I mean, here, you know, for the Toda, so let's not talk in general. I don't want to do that. I mean, so for the Toda, it's obvious because you see when you increase n, I mean, then the range. You know, the support will be increased, and therefore they cannot be functionally dependent. No. I mean, if I have, let's see. Oh, you're still looking at this n. Yeah. No. Sure. I mean, as I said, I mean this. Okay, so maybe I should put here n equal infinity. This for the infinite system is the definition for the infinite system. Yes. Yes, that's an operator equation, yes. And you see, you know, once you have this, then of course it's clear that the Qn is conserved, right? If I do a sum here, then the change of Q will be only through the boundaries, because inside, I mean, these currents are simply canceling, right? So it's a sum which cancels. Okay. Yes? Well, I mean, so okay, yes, but you know, here the logic is the following. I mean, so I require for my charges to have a strictly local density. Then these objects, if they exist at all, they must be local, right? Because when I work out the commutator, the Poisson bracket, it's just a local quantity. You know, if I take I take H, which has a local density, and if I take another Q, which also has a local density, and work out the commutator, it will be has also a local density. Yeah, no, okay. Maybe I sort of assumed that sort of, I mean, yeah, sure. I mean, this okay. So maybe I should have said this sort of more clearly, but I'm sort of always, I want to think Toda. I'm always pointing at this thing. It's clear that they're just. I mean, that's what you mean by density, right? Yeah. It's a homogeneous system, right? Yes. Well, I mean, no, I mean, finite. No, but what is important, of course, is that it has a finite support. These are strictly local quantity. This is very important, right? I mean, if I would have something which has sort of long tails, I mean, then you could still maybe study generalized hydrodynamics, but maybe not so good, yeah. I don't know. I don't want to go. Sorry, I mean, I don't want to go into generalities. I just want to say that this is what I do, and then for the Toda, it's satisfied. Okay. What is? I don't understand. What is the question? I mean, sorry. Yeah. Yes. 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 Well, it will matter, yeah, in general. I mean, a priori, I don't know. At the moment, all what I know is that they have a density, and the density is strictly local. We will see. I mean, how it continues. Okay. All right. So now I have a definition of this. Okay. All right. So now the next chapter is also sort of an introductory kind of thing, which is the two-particle phase shift. Okay, so now I have to use some color. You can see this better. I mean, so here is my XT plane, and now let's say I have just two particles. So let me first take the case of two particles too. And so maybe I have one particle which is coming along like this, and then maybe I have another particle which is coming along like this. Okay, and so as they come closer, so this is now the solution of my Toda lattice with two particles. Okay, so they come closer, and then what they would do if they are sort of just non-interacting particles, they would continue like this, and this one would continue like this. Okay. But in fact, that's not what they really do. I mean, sort of, it moves like this, and the other one maybe moves like this. Okay. The point is that they are shifted. So asymptotically, they will still be moving with a constant velocity. In fact, as you can see from the picture, if this is V1 and this is V2, then this is actually V1 and this is V2, right? So the order, if you want to, is sort of interchanged. But then on top, I mean, they are sort of displaced by something of order 1. And this order 1 is the phase shift. Of course, this picture would be true also for any other interaction potential. But when I go to 3 particles, then of course it will be very different. I mean, so I'm of course having back of my mind that I want to do more particles. Okay, so this is what is called the phase shift. So that's a shift by order 1. I mean, I can also think if you sort of think it more like in the time direction, you can also think of this sort of like a delay time. So I mean, this one is sort of moving a little bit slower than it should, or maybe it's moving a little bit faster. So the phase shift clearly does not have any particular sign. And for the Toda lattice, so it's always Toda. I mean, so let me just sort of say the Toda lattice. I mean, the phase shift phi It's actually because of sort of Galilean invariance, it's a function of the difference. And it turns out to be 2 the log of V1 minus V2. So this is already what Toda knew. Okay, and now I want to do the same thing for several particles. So maybe I allow myself to erase this a little bit and keep here the V2 and the V1. And now I want to do the same thing for 3 particles. And well, they are coming in. I mean, so maybe maybe this one is coming in, this one is coming in, and then maybe this one, and maybe there's another one coming in here. I mean, so now I have velocities v1, v2, and v3. Okay. And now, of course, I can still sort of start, sort of put this potential sort of lines here. I mean, and then this one here. So this is the V3, that's the V2, and that's the V1. Now, I carefully put it like this because you see now in this intermediate region, when I have an interaction, so somewhere over here, I mean, the motion in here could be extremely complicated. But if I wait, I mean, then eventually what I'm going to see is again, I mean, this outgoing velocity, so there will be V3, V2, they are now, so the order is reversed. And on top of this, I will see a phase shift, right? I mean, so the true trajectory will be sort of shifted somewhat, and this will be also shifted somewhat, okay? And this is a very beautiful theorem by Jürgen Moser, who proved this for the Toda lattice. I'm always talking Toda lattice, okay? That's Moser, 1975. I mean, he gave a very nice argument, and he proved that for arbitrary n, this will be always true. And that's sort of the important point, is the phase shift is now not some complicated function of all the incoming velocities, but the phase shift is additive. So phi is additive. If I want to know what is the phase shift of 3, then I just look at my table. The phase shift is this logarithm, and there will be a collision with V2. I mean, so I have to take this one, and then I have to add the one which comes from the collision with V1. And then this will be the phase shift of V3. That's, of course, the hallmark of integrable systems, that, of course, you have a non-trivial phase shift, but this phase shift happens to be simply the sum. Now, if you're sort of at that moment sort of not completely sure how this works, I mean, there's sort of a limiting case which is actually instructive. So there's a limit case which is actually a limit of the Toda, but I don't want to put this into any formulas. There's a limit case of hard rods, where rather than having the exponential potential, you imagine that on your line you have sort of little rods like this, and they have a velocity, and they do the obvious elastic collisions. Okay, and in this case you can sort of see this picture sort of more easily. So if this is x and this is t, and here I have maybe one of them coming, and then maybe the other one is coming like this. And then, of course, they move freely, but then as we reach exactly the distance a, so this is now my hard rod length a, then, this one will simply jump over here, right? And it goes like this, and this will simply jump over here, right? I mean, so you see that in this is sort of the limiting case where this collision time has been shrunk down to 0. And the additive nature, I mean, you can sort of read off more or less, sort of visually. I mean, you don't need any proofs for that. Okay. Now, the hard rod system is actually one system which falls under to this general class because it's the limit of the Toda, and the Toda falls under this class. But the hard rod system by itself has been studied actually in great detail by Dobrushin and co-workers. Let's see, I guess the first paper was, Dobrushin was very fond of that topic. I mean, he worked years on it, and let's see. This is 1983 already. Okay, there were later papers, but this is presumably the first paper he wrote. And for this system, you can prove whatever you want. I mean, you can establish, the generalized hydrodynamics, and you can prove the validity starting from microscopic motion. But the point is that in this case, the phase shift is very, very simple. You see, the phase shift here is just jumps from this point to this point. And so the phase shift phi is just a number. It's just equal to a. And it's independent of the velocities. And that, of course, simplifies enormously. Once the phase shift depends on velocities, it will be a totally different world. I mean, it will be more complicated. Of course, if I have the general scheme and then go to the special scheme where phi is equal to a, I mean, then you just recover what Dubushin did. It's just a one dimension. It's just a label. J 1, 2, 3, 4, 5. Okay, I'll come to the lattice. Actually, it's sort of already on the next line here. Then you will see how the lattice goes. Yes. No, okay. It's a good question actually, but I will do it in a second. I mean, it's already here on my notes. Okay. Well, that's a riddle, but it's any experience. I mean, you take any one of the non-integrable quantum chains, right? Then what are the conserved quantities? I mean, typically you have, you always have the energy, so n equal to 1, and then maybe you have one spin component, and you have n equal 2, and then that's the end of the story. I mean, you just don't have any further conservation laws. Maybe you were not clever enough, but you don't have any further one, right? Okay. So now I come to point 3. Which is a basic tool, which is the lax matrix. And now you see here, I was talking general. I mean, but now I have to give you a specific formula for this use. And so here we have the charges. The charges is just sort of convenient shorthand and the columns, right? So the main point is that once we have the lax matrix, then there are simple formulas for these quantities, and that's of course very useful if you want to do any sort of theoretical analysis. Okay, so let me first sort of say a few words about fluid and lattice. I mean, you see, Toda called it lattice because he was thinking of a discrete wave equation, and the way I was drawing the pictures, I obviously was drawing here pictures of particles in physical space, and so this was sort of the fluid picture, right? And so I mean, this is sort of the first picture you think about. But now let me sort of that's also your question. Let me sort of say one word about the lattice picture. And so we introduce the stretch, which is Rj. It's just a definition of Qj plus 1 minus Qj. And then you decide to rewrite your equations of motion in terms of the stretches. I mean, so sometimes people call this also free volume because it's a volume between between the particles with neighboring lattice index. And so now you can write this as pdt of Rj. Well, that's easy. I mean, you just differentiate. So that's Pj plus 1 minus Pj. And then you look at Newton's equation of motion. And that gives you the change of momentum. And this gives you minus e to the minus Rj plus e to the minus Rj minus 1. Okay. So you see, the positions have disappeared, and I can think of this as a closed system for the stretches. It's second order, so if I differentiate this again and then plug this in, then you see that you get a nonlinear wave equation, right? And so in this picture, I mean, you think of your lattice as just sort of the one-dimensional lattice, 1, 2, 3. So this is my lattice C. Okay, so here's maybe the lattice Ij. And at every lattice point, I mean, you have the variables Rj, Pj. I mean, these are sort of your field variables, if you're right. I mean, it's sort of like position and momentum, but anyway, I mean, you know, it's that particular system here, and now you look at the equation, then you see that, you know, I mean, here you get a coupling to the right. I mean, maybe you cannot see this. I mean, so there will be one coupling to the right. I mean, that's the equation of R dot, right? And then there will be a coupling to the left if you look at this, because this is J minus 1, and then this corresponds to the PJ dot, right? So it's just the nearest neighbor lattice system. And of course, if you think in terms of quantum mechanical systems like, I don't know, XXC, you know, this would be sort of the natural picture. And actually what I'm going to do, I mean, this will be always in the back of my mind, right? I mean, so now I'm really thinking of a discrete nonlinear wave equation. Okay, fine. So now the question is, what about this conserved quantities? And so now let me take the lattice size 1 up to n. I mean, that's just convenient at the moment. And let's say I take periodic boundary conditions. I'm not writing out how you do this exactly, but sort of more or less the obvious one. And now there is sort of something which are called the Flaschka variables. So, you know, you just look at the system and you see that here the R really appears in the exponential. And so rather than using now the P and the R, I mean, you're using slightly different variables. I mean, the first one is really like P, and the reason why I put it is, you know, that sort of, I mean, that's just a canonical notation. It's sort of easier to remember. I mean, so the Bj is nothing else but Bj, and the Hj happens to be e to the minus Rhj over 2. So it's over 2. I mean, so the A squared is actually what appears in the interaction, right? I mean, so when you look at this thing here, I mean, that's sort of the intuition behind it. When you look at this thing, you see this is written as B squared plus A squared, right? All right, and then Flaschka was at the Courant Institute, so he knew about the Lax matrix, and his question was, is there a Lax matrix? And indeed, there is a Lax matrix, and so let me first write down what is the Lax matrix. So this is, well, we are still at finite volume. So this is a triangle matrix, which looks like this. I mean, it's 0 all here, and then out here, because of periodic boundary condition, you have also one matrix elements, but let me just ignore this. And for a given system, I mean, you know, what you put on the diagonal are the B's, and what you put on the first two off diagonals are the A's. And so that you see that Ln transpose is equal to Ln, right? So that's the Lax matrix for this system, which, you know, at the moment it has no deep reason why you introduce this, but you will see in a second an equation why it's so extremely useful. Okay, so it's a tridiagonal matrix. Of course, the matrix elements evolve under your dynamics of the Toda lattice. So it's a time-dependent tridiagonal matrix. All right, and then we have to introduce another matrix, which is usually called Bn. And, you know, it's of the same form. So out here I have all 0. The diagonal I put also 0. So 0. And the off diagonal I put here A. And this off diagonal I put minus A. So the Bn transposed is obviously equal to minus Bn. Okay. All right. And now comes sort of the important result, is that when you look at ddt of Ln, and this happens to be the commutator of 1/2 Bn Ln. So ddt Ln means evolving according to the Toda lattice dynamics. And if you make this definition, you discover that there's sort of a matrix, a simple matrix equation which which is satisfied by this Lex matrix. Now, why is it useful? Well, you see, this is sort of anti-symmetric, and of course it's all time dependent. But from this, it follows that the eigenvalues of Ln are conserved. You see, it's very easy to actually find the eigen, I mean, at least conceptually, it's very easy to find the conserved quantities. I mean, all what I do is I take this Lex matrix, you know, I diagonalize it, I look at the eigenvalues, and these are the conserved quantities. Questions? Now, these eigenvalues. Okay, so let me, I guess I have, maybe I use, okay, maybe on, okay, now I don't have a notation at the moment. Okay, so the eigenvalues are non-local. See, if I, you know, if I want to have to, if I change a little bit my A's and my P's somewhere, even far away, I mean, then the eigenvalue typically will also change. So the eigenvalue will depend, so to speak, on all variables. You see, it cannot just depend on a few, right? I mean, maybe it depends very little on eigenvalues far away, but I want to have them local. I mean, they are certainly not local, right? Okay. And so the question is whether you can sort of produce local quantities, and the answer is yes. Let's see, I guess I have to switch to the other side. And how do you produce something which is local? Well, that's very easy, fortunately. Now let me introduce I mean, at the moment it's still sort of for the finite system, but let me use already sort of, yes, there's a question. Because well, it's if you take a Hamiltonian, and well, no, if you take you know, if you take an operator and you apply a unitary, then the eigenvalues do not change. This is a generator of a unitary or of an orthogonal transformation. Well, it's time dependent, but you know, it's nevertheless it's sort of a sequence of unitaries, and therefore the solution of this equation. So you know, I mean, what I'm saying is that the solution of this equation is Ln of t, right? But this Ln of t is unitary equivalent to the Ln times zero. Okay. That's fair enough. It's an anti-symmetric matrix, so the exponential will be something which is a unitary. Okay, so let's see. Okay, so now I have the charges here, and the trick is the following. That okay, so now okay, maybe sorry, maybe I want to do it slightly differently. Maybe I want to erase the title also. Then that's much yeah. So now I'm sort of writing this already for the infinite system. So now I have again n equal infinity, and my conserved arch n is really I take the trace of L over n. You know, of course, this trace doesn't exist, right? I mean, because you know, then now it's an infinite matrix. If I would do this at a finite, then of course, you know, I could write this for the n. Now maybe I could have. In the finite case, of course, it's a well-defined thing. I mean, I just take Ln to the power n, right? But let me do this. I mean, so now I can look at the densities. And what are the densities? Well, I mean, you know, the trace is simply a sum over the diagonal elements, which is exactly the sum structure which we want. I mean, so I take Q super n sub j will be nothing else but the nth power of L, and then I have to take the JJ matrix element. I claim that this is a strictly local quantity. Why is it strictly local? Well, I mean, you just sort of work out the matrix, and this looks like this. I mean, so now I put C in this direction. So maybe here's 0. And you know, I have to apply this matrix n times. So I do n steps down here, right? N steps. It's a triangle matrix. So let's say if I'm at latticide 0, then, or maybe at latticide J, but I mean, let's say at latticide 0, then I can either go up, I can go straight, or I can go down, because it's a triangle matrix. So, if I want to get support, as far as largest support, I mean, then the only path which so of course, when I expand out, what I mean by L to the power n, then I will get a sum over all random walks, which sort of start necessarily, let's say, at J, well, maybe I should have called this J, and end up at J. And so it's a sum over all random walks, which can have these 3 steps, right? I mean, so, it's somewhat lengthy sum, but anyway, I mean, depending how large n is. But the main point is that, if you think in terms of support, I mean, the worst case is that I go up, but, eventually I have to come down here. Otherwise, I mean, I will get no contribution to this term. And so eventually I must come down here. And so if this is n, I mean, then this is something like n over 2. Right? So you see that when I do this sum, I see that I'm summing up whatever is sitting in this matrix, right? I mean, so a sum means that it's sort of a product of these entries, right? I mean, either the A's or the B's. So at each lattice point, or at each bond, I have sort of sitting an A and a B, and as I'm summing, I'm summing all this contribution. So it will be some complicated function, of course. But since the random walk cannot go further than n over 2 away from J, it must have a strictly finite support. And you can also see why as I increase, I mean, then as I go from n to n plus 1, then of course I can go a little bit further. So then, I will have a worse support, but it's just increasing. Every step is sort of increasing by 1 unit. To what? Yes. I don't understand the question. It's to what? Of the phase shift, yes. No. I mean, here, well, I mean, it depends which system you look. I mean, here you have to solve the 2-particle Toda lattice, and you get this answer. And if you do the hard work, I mean, obviously, they're just shifted by A, so then you get this answer. This follows directly from the 2-particle dynamics. Phase shift is a property of the motion of 2 particles. The integrable, yeah, and you just have to solve the two-particle equation, right? Okay, fine. So now we are here. Okay, now once we have the charges, I mean, then you can also work out what are the currents. And since we have an explicit answer for the charges, I mean, we can work out the currents. And I'm just going to use this equation here, right? I'm not going to do the computation, but you see, I mean, I have identified for you what is the QJ, and therefore, I will be able to compute what are the currents. It's a very simple computation, but you cannot find it in Toda's book or in any other book. I mean, not because people were not able to do this computation. It's a 2-liner. It just tells you that the idea of focusing on conservation laws and generalized hydrodynamics was sort of very far away from the kind of things they want to do. Okay, so let me just tell you what so I'm just using DDT of Q super n. I mean, with this definition at time t, I mean, this is now a perfectly well-defined quantity. And of course, what I must find is that this is Jj over n minus, wait a second, maybe plus 1, never. Okay, this way, okay. Okay, and then from this I can determine what is the current density of the nth conserved quantity, and it turns out to be the L to the power n. There's a factor 1/2 here. Then there's the L off diagonal, and then it's the JJ matrix element of that. Yes. Okay. Okay. Yes. Yes. It's just an infinite dimensional tri-diagonal matrix. It's infinite, yeah. It's just the sum, you know, it's just I've erased already the Hamiltonian. If I write down the Hamiltonian, it's an infinite sum, right? I mean, formally, yeah. So the trace of it's clearly infinity, right? But it has a finite density, okay? So okay, you know, it's just like the Hamiltonian, right? I mean, if I write the formal sum over all j, I mean, it's certainly, yeah, that's right. Yeah. Well, okay, so you have to okay, so what does this mean? It's L n times. Let's say 3 times, right? Now you okay. So let me maybe like this, and then it's the JJ matrix element of this, and then I insert, let's say, J double prime. And then I insert the J prime. So now I'm using sort of the more quantum mechanical notation, right? I mean, so this is, and then I do the sum over all of J prime and J double prime, right? This is what I mean by the cube of the matrix. Well, if you interpret these terms, it means that, you know, each term in this sum I can interpret, you know, as a random walk, because you know, this matrix element is a tri-diagonal matrix, right? I mean, so, you know, if I know that I have the J here, the J prime can take only values J equals J prime can be only equal to J plus 1 or J minus 1. And so if I write this, I will get the sum over all random walks. And you know, if I specify the random walk, then from the one particular trajectory of the random walk, from this I can deduce which kind of term I have in this sum. And if I sum over all random walks, then I get this. Now the claim is that when I do this sum, that, you know, you look at this path, and you know, because it's bi-diagonal. I mean, the L is bi-diagonal. You know, I cannot go further than n over 2. So the variables in this sum which I pick up can never depend on anything which is sort of, you know, up here. It will only depend on variables which are you know, all these pairs are sort of, you know, these sums are all sort of, you know, dynamical variables which have a lattice index. And I will never find a lattice index which is above J n over 2 and below J minus n over 2. What was that? Okay, so I was interrupted by questions. I mean, so this is L to the power n, and here comes the L off diagonal, which I have not explained. I mean, the L off diagonal simply means that I take now again at phi diagonal matrix 0 along the diagonal, and has A is along this one, and has A along this one. This is sort of the off diagonal piece of L. I mean, that's the expression. Okay, fine. So now let's see. How are we doing with time, actually? Okay. But that's okay. Okay, so now I have the currents, and I have the charges. I have the conserved quantities, and well, then you see that actually I missed something. You see, because when you look at the equations of motion, there's still yet another conserved quantity which is not covered by the Lex matrix. And if you look at this equation, right? I mean, this is obviously of a conserved quantity, because here I have you know, sort of this difference standing. Okay, and so therefore, what you find is that there's yet another one. So conserved currents. Let me erase this one here. Plus, I mean, the Q0 of J, which is simply the stretch, which is RJ. And then, of course, I can also compute what is the current of the stretch. Well, this is minus PJ. That's you know, it's an unusually conserved quantity, because its current is self-conserved. I mean, that's you know, by definition, what I wrote you is nothing else but the Q1. Right? If I take the Q1, then it's a trace of L simply. That's just the sum of the diagonal elements. The sum of the diagonal elements are just exactly with a minus sign, simply the momenta. So if I look locally, it will be just the momentum. All right, so now we're in good shape, and so now the next thing is the lex. So EOS, this is the density of states. That's just a standard thing, and then comes the hydrodynamics picture. I guess this will be the last chapter for today. And let's see. Okay. So let me look at the finite system again. So I have Ln, so that's my lex, and then I will have eigenvalues. I call lambda L. I have eigenvectors phi sub L in the L. And I look at 1 over n. I look at, let's say, the nth conserved quantity. Well, it's a trace, right? So this is 1 over n, summation L equal 1 up to n, the lambda L O n. The trace, if I go to the diagonal basis and compute the trace, then it's just sort of, I can take the nth power very easily, and this is what I get. And this I can write in a slightly different way. This I can write in a slightly different way by writing this as integral over W. And then I write this as 1 over n. It is a summation del L equal 1 up to n. I do a delta of x, delta of W, minus the eigenvalue was called lambda L. Okay, and then I put here the W to the power n. So if you work out the delta function, that's just exactly what I wrote. Okay. Now you look at this quantity here, and this is the DOS. So that's what people would call the empirical DOS. See, I look at one realization of my A's and B's, or one realization of the R's and the P's, and then I will get these eigenvalues, and then I sort of represent them simply as the sum of delta peaks located at the value of the eigenvalue. So this would be for finite n, I have just n peaks, and this would be sort of the finite n empirical DOS. Okay? All right. So now let's think about the thermal case. So let's now imagine that I put my Gibbs distribution with the usual e to the minus beta h. This will be much more discussed later on, but this will be tomorrow. So maybe I have to look at the GGE for this purpose. But let's think thermal, right? So if you think thermal, then L becomes a random matrix, becomes a tridiagonal random matrix, and this is the empirical DOS of that tridiagonal matrix, right? So now the eigenvalue, now the matrix entries are, have a very specified distribution. For instance, the thermal distribution. I will discuss this in more detail, but I just want to get to the point of this density of states, right? Well, you see, if for such kind of distribution, the DOS is self-averaging, and it will almost surely go to a deterministic limit. Okay? So this thing will be self-averaging. Just meaning that when that fluctuations sort of go to zero, and in fact it will converge as n goes to infinity to some smooth density rho q of W, and the moments of this distribution, so the rho q by constructions, I mean the rho q is larger than 0, and the integral over rho q is equal to 1. So the moments of that distribution will give me just in the infinite volume limit will just give the expected values of the densities, right? Or if you want, so sort of, you know, of the average values of the energy in this case. Okay. So then you know, if I look at this quantity here under the thermal distribution, you see the thermal distribution means that actually, you know, it's a rather simple distribution. I mean, you know, the matrix elements are just independent random variables, but the observables we are looking at are actually quite complicated because, you know, if I take large n, I mean, then this is a rather complicated function. But the assertion is that this average I can actually compute by looking at the nth moment of this asymptotically self-averaging density of states. So rather than looking at these expectations, actually it's much more convenient to think of this function, which, so to speak, you know, it's sort of perfectly equivalent. It's just sort of like, you know, probability distribution under decay assumptions. You know, you can either think of moments or you can think directly of the density. And so I'm just saying that the density is actually, for formulating the hydrodynamics, is much more convenient than looking at the moments. Okay? And so now comes our picture. So what is the hydrodynamic picture? Well, I mean, the hydrodynamic picture is that is roughly the following. I mean, you know, you take one of these initial conditions which I explained to you, and then I'm going to look at not too short a time, and then I'm looking at time t. I'm looking at that particular configuration, right? This will be fairly noisy, and presumably I will not easily to sort of figure out, you know, any kind of sort of simple description. However, if I now, rather than looking sort of, you know, microscopically at this configuration, I'm now constructing the Lax matrix. So here's my system, okay? So it has many particles. Okay, but now I'm taking a little block over here. Let's say I take a block of 500. And I'm looking at the empirical Lax matrix in this block here. And now, of course, there will be another block. I mean, there will be slightly different empirical Lax matrix, right? And so I'm looking at these blocks. And now the assertion is because, you know, these eigenvalues are connected with conserved quantities. These are actually the slowly varying objects in this somewhat complicated dynamics. So as I go to the next time step, then I will see, you know, something more complicated. But the point is that the local Lax, I mean the DOS, I mean the density of states of the Lax matrix will be slowly changing in time. That's the picture behind the hydrodynamics. And then, of course, once you have this, I mean, then you hope that you might get closed equations for this type of quantity. So let's see, what is, okay, I'm still going to this time. Okay, so let me sort of do this maybe sort of slightly more detail. I mean, so, and then I will still pick up this idea sort of tomorrow. I mean, so if you really want to go to a quantitative description, you see, you don't need only the average values of the conserved fields, but you also need the average values of the currents, right? Otherwise, I'm not able to, you see, I mean, on a macroscopic scale, we want to write down sort of something like an evolution equation of some density plus dx of some current, which itself depends on the density, okay? So this would be the case of a single conserved quantity, which is conserved. But now you see, I have an infinite number of these variables, and so I have to extend this kind of simple conservation law to an infinite system of conservation laws. I mean, for each n, I will have such an equation, and they will be sort of functionally dependent, right? So what? How does this functional dependence work out? Well, I mean, the point is that, you know, when you so now, you know, you have to think about these currents, right? I mean, so you have to think these currents. In fact, you know, I have to look at the average currents. Maybe, you know, for first step, maybe, you know, average with respect to the thermal one, or maybe with slightly more general things. Anyway, I mean, so So I have to study these currents. And so now I can look at I can look at it again at the same expression. Let me maybe just really write it down, because otherwise it's sort of well, let me keep this. Let me just write it down, because otherwise let's see what I'm doing. Okay, so now I want to take 1 over n, and now I take the trace. So now I'm looking at the currents, right? I mean, so I want to look at the average value of where are they? Here, of these quantities. Okay, it's L to the n times L off. Oh, it's a factor 1/2, which I omit. Okay, and then of course I can invite this as a sum over 1 over n. But now you see that because I have this L off, I mean, it doesn't suffice to actually know the eigenvectors of L. I also have to, the eigenvalues, but I also have to know about the eigenvectors, right? And so if I write this like this, I mean, then I get L equal 1 up to n. I get the summation j equal 1 up to n. And then I do already this simple delta function. So, trying to sort of do the analog of this thing. So there will be delta and L. Okay, but now I have this funny off diagonal. So I have to work this out, what this actually is. And so I have the W to the n. I mean, that gives me this operator. Now this operator I just have to expand in the eigenbasis. So I get psi L at the lattice point j plus n, and then I get psi L at the lattice point j. And when I do the computation factor, there's no factor 1/2. So this is completely correct. And then because I'm doing sort of one step here, I mean, so I will pick up an extra HJ in this notation, right? Now this is sort of again sort of like an empirical carbon density. And in the limit as n goes to infinity, it will be again self-averaging. So it's self-averaging, and there will be an almost sure limit. And this is something which I call rho sub j of W. So it's the same formula as over here. If I want to compute the nth moment of the current, it will be just given by the nth moment of this particular density. Now, you see, I have these matrix elements here, and so here it's obvious that it must have this positivity and this kind of normalization. Here it turns out that when you look at these things, I mean, there's no reason that it should be positive. And in fact, when you put n equal to 0, then you see that I have the trace of L off. But the trace of L off, I mean, this is an off-diagonal matrix. I mean, so it's simply 0. And so, what is sort of the normalization here to 1 would be here the normalization to rho u, rho j of W. W is equal to 0. But empirically, we have done numerical simulation on these things. I mean, you should think of this empirical density. Let's say for the thermal distribution, this is sort of this looks like a Gaussian or some deformed Gaussian, but it's a rather nice looking function, and similar these objects over here. So you should not think of them as sort of something very rough. It's sort of a smooth function of the W. Okay, now, but the point is that you see what we want to have is now that. Okay, so now we have. Okay, so you see, now comes sort of the difficult point. I mean, you see, eventually I want to write down closed equations for the density of states of the conserved charges, and so what is required. Well, look at this equation. I mean, if I start generalizing to several components, I mean, then I have here a list, let's say, of 5 densities, and then of course, I have 5 currents, but the currents are some nonlinear function of the densities, right? And so that's the same kind of stuff here. So what I must find is that the rho j this current DOS, I mean, this quantity, which sort of, it's sort of a convenient labeling of the average currents, this quantity must be given in terms of some complicated functional of the rho J, sorry, of the rho Q W, and because I have infinitely many variables, so this is something which goes over all. Right? It will be a complicated functional of these densities, right? And I hope I will write down for you what this functional actually is. I mean, here it looks sort of very abstract, but if you go a little bit further into the theory, I will write it down for you very explicitly what that functional actually is. Now, if you have this relation, you see, then at least in principle, you can start to write down the hydrodynamic equations. And so let me sort of do this sort of slightly formally. I mean, and of course, many details have to be filled in, but at the end of this first lecture, I just wanted to show you at least sort of what are these hydrodynamic equations. So now everything depends on x and t, my space-time point, right? So here's x and t, and at every lattice points, I have sort of this infinite set of conserved quantities. And now I want to look at their evolution. And so what I have is I have my average density. So this is the new. I didn't introduce that yet. I mean that's sort of just the average stretch. Let's say at 0, right? Okay. So now the new will depend on the space-time point. I mean, so now I have my first equation is ddt. Well, let's say partial t of nu of x and t. So that's just in terms of these labels. It's just a scalar quantity. It just depends on space-time. And then there will be a minus dx. And now, of course, we figured out already what the current is. So the current, I can just, it's just the first moment of the Q. I mean, so that's easy. So that's the integral over W. Then I have the rho of Q. I mean, the density of states for the conserved charges. Okay, so now I have to sort of put here sort of, first of all, the label, that's the W. And then, of course, it's at some space-time point xt. And then I have to take the first moment, and that's equal to 0. Okay, so that's your first hydrodynamic equation. And now the second hydrodynamic equation is an equation for this rho Qs, right? I mean, so it will be at space-time point, and it will be, labeled by the W. So this is now a function which depends on one-dimensional space-time and on the label, which in our case is just one-dimensional, right? And well, what is it? Well, I don't know. I don't know what it is at the moment. I write it formally. It's just sort of dx, and then it will be. It will be the rho. I mean, this current DOS, one which we sort of worked out here. Well, the same arguments x t. Okay. And now, of course, it's not a closed equation, right? Because I mean, this is closed, but well, I mean, this is well, it's not closed, but it's expressed in terms of the rho Q. So the rho Qs appear over here. So now, of course, here I have to put in this functional relationship. If I put in this, it's just sort of like putting in here a nonlinear function. So it's just a more complicated thing. I put it in here, and this is sort of my generalized hydrodynamics. So that's sort of a fairly good point to stop. Actually, I can still use a little bit of time. I mean, if the chairman allows me to use some of the questions time, or can I still have 5 minutes? I mean, because I mean, then it would be much nicer, sort of, and then maybe the questions we can sort of answer afterwards. Okay. All right. So this is what we are aiming for now. Now, the first thing what you want to do, even, wondering about, solving or anything, I mean, you want to write down what are the equations, which means that in particular, you want to write down what is this functional relationship. And then somehow, we don't have any good handle on this rho of Q yet. But the point, what I want to emphasize is that, and this is what I have to take up next time, it's a static computation which we have to do. You see, when you look at these things, I mean, these are sort of, I mean, for instance, in the thermal state or later, and we need actually the GGE, but these are computation without any dynamics. We have just to sort of solve, this statistical problem and figure out what is sort of the empirical densities of this Lax matrix, right? I mean, so this will occupy sort of tomorrow for quite some time. But the last point which I want to make, I want to sort of give you, besides this equation, sort of a more intuitive picture of what is actually going on dynamically in this system, right? That's sort of the last part, and this is just sort of trying to pick up to what I'm just erasing here, namely this particle phase shifts and all these kind of things. So what is the picture which we have? So now I'm going back to the fluid picture. So here I put my X and T phase, and now I have all these particles, and now they do sort of this complicated collisions. However, you see what's happening is that in this space-time I can sort of hopefully localize sort of reasonably well-defined local regions. Well-defined local regions where maybe in this small region I thought this as a space-time region because I mean it's extended a little bit because they have to come close. It's also sort of in time. So maybe here I have a small region where I just have two particles, right? I mean, so there will be sort of one trajectory coming this way, and then there will be maybe another one going out this way, right? Okay? I mean, the only thing which I know is that with some small error, but this is hopefully exponentially small, I will see that here that these velocities are the same, and I know that there will be this phase shift, right? And then there will be some other region over here. And then maybe I have 4 particles here, right? I mean, it will be a more complicated region. And of course, so I have now, what I'm assured is that in a good approximation, I have here 4 particles coming in, 4 particles going out. Right? And you know that the order, I mean, the velocities up here are exactly the same velocities up to order as which they are incoming, okay? So now if I go to a somewhat larger picture and sort of forget about these details, I mean, sort of these extra drawings, I mean, I have, somewhere sort of, not a zero density, but sort of some reasonable, I mean, the assertion is that it should be true at any density, but I mean, let's imagine for the moment that it's sort of, not too high density. I have sort of this interaction region. And in between these interaction regions, of course, the particles are moving essentially along a straight line, but they have picked up their phase shift, okay? And so to understand what's actually going on, it's useful to actually draw one single particle, which I sort of insert over here, and I insert, with a definite velocity, which I call V, okay? And now I just want to follow this particle, and let me draw it on the other side, what it will look like. Otherwise, it's sort of, blurring. Okay, so this will go a little while along a straight line. I mean, that's fine. Okay, so now maybe it hits sort of this kind of interaction region. Now, you see, once it's interacting, it loses its identity. I really don't know what's going on because, it's interacting with other things, and what I call V is, of course I can follow the label, but the label is totally wrong because this will go out with a different velocity. So I must make sure that this incoming, for instance, this one, I must connect to the one which is sitting up here, right? And so here there will be a little bit blurry, but what I know up to, either sort of, let's say up to a spatial shift, it will sort of, so here's some blurry region where I cannot identify, but then hopefully here there will be another stretch that will have exactly the same velocity, and then it's sort of in between, it does something complicated, but the effect of this complicated thing is that it will be just shifted by an amount which I know. Right? And then, which I know, I mean, it depends on with what kind of particles is interacting here. Well, and then I just keep going, and then you see that it might be shifted to this one. Here's some complicated thing. And of course, if I actually really look at the numerical realization, maybe I have initially maybe I have a hard time to actually identify what is the trajectory of these particles, right? But the picture which we have is sort of that you have these particles moving, but of course so an individual this is something which people like to call maybe a quasi particle, or if you think about hard watts, I mean, they usually call this a pulse. It's just meaning that I'm trying to follow so the trajectory, not the labeled particle, the trajectory is a definite velocity. Okay? And now the assertion is that if I look at these things, they basically sort of move. They move with their bare velocity, which is the v. So the v. I mean, that's the bare velocity, right? But they do like a random walk. I mean, they sort of once in a while jump to the right, and then once in a while they jump to the left, or with some time delay, but it's sort of hopefully reasonably spatially localized, they sort of jump back and forth. And if this picture is true, which of course, when I do the hard rod case, which I erase over here, there it's sort of literally true, but in this case it's sort of more complicated, then this sort of gives a fairly good dynamical description of what's at least sort of physical intuition of what the dynamics actually consists of. Okay? Now, tomorrow, so this is a nice picture and it's very useful, but it doesn't lead to any formulas. Okay? And so what I will do tomorrow, I will sort of come back to the task, namely, how to get the whole Q and how to get maybe also the whole chain. So thank you very much.
Questions or comments?
Well, I mean, the assertion is that in any integrable system, there will be an underlying quasi-particle pictures of that type. No, I think it's more like sort of. Well, I mean, maybe other quasi-particles. I mean, I just want to say that you see this, for instance, this picture you can use in order to make sort of like even for quantum system, you can use it to make sort of like a classical simulation. You see, rather than simulating the full quantum system, now I'm claiming that same picture remains true for the quantum system. And the way how they jump, I mean, depends on the interaction, but this picture is sort of universally valid. So you can use this picture even for the Toda lattice. I mean, you can use this picture to make a fast simulation in the sense that rather than simulating all the many particles, in which quantum mechanically you could do not anyhow at all, right? You simulate this interacting system, right? I mean, so. No, I mean, yeah, I know, the notion quasi-particle is not such a good notion because, it's used widely and nobody really knows what it is, right? I mean, but here it has a very, I want to say it has a rather definite meaning, and that's what. No. Okay.
Questions or comments?
Could you clarify whether is it the label W that was playing the role of the velocity there?
Yes.
Oh, okay.
So, well, I mean, it's really the stress velocity. I mean, so it's not really the velocity, right? But it's very close to the velocity. It's sort of like yeah, okay, it's related. But maybe, yeah, okay. I mean, okay, it's true, but another way to think about it, it's just rather than looking at the moments, it's sort of a convenient label to for which you have sort of it's a convenient coordinate to write down these equations. You see, I mean that's maybe another way. I mean, you don't really. I mean, of course you could, but sometimes people call this a spectral parameter. Then it's sort of a more neutral word, right? I mean. So you can also think that rather looking at these moments, which at the first sight, I mean, the QNs, which was initially sort of might look like a natural thing. If you want to write down the QNs, for the QNs, the hydrodynamic equation will look rather messy, right? Whereas once you have written it in this particular form, and in particular, if I specify this for you, it sort of looks more transparent, right?
Yeah, questions or comments? Okay, if not, let's thank. You have? Oh, no. If not, oh yes.
Well, I mean, this will come during the week. I mean, so yeah, I mean, you know, I mean, not Toda lattice. I don't know about any physical realization, but when you come to quantum integrable systems, I mean, they are your neighbor. You can ask sort of immediately, and he will give you some instructions on this, right? I mean, so you know, people can actually produce these kind of things in the lab, and you know, can compare sort of measurements from the lab directly with predictions from generalized hydrodynamics. No, I mean, you know, it made a big impact on the community, right? I mean, so, but not. You have to go to. I mean, not just Toda, right? I mean, Toda. I don't know any sort of direct good physical realization, right?
Okay, maybe we don't have any other questions. Let's thank speaker again.